I want to have a chat about how we can use a chiral auxiliary to control the diastereoselectivity of an aldol reaction as a way of getting an enantiomer-enriched aldol product in the end. So just as an example, I've got the scheme at the top of the page. Starting with the ethyl ketone on the left, I need to do a selective enolisation. I'll come back to the details later, but once we have our enolate, so just here I've drawn the Z enolate, the plan is to react it with an aldehyde. So the enolates are nucleophile, the aldehydes an electrophile, and we'll do an aldol reaction to form a new CC single bond to form a hydroxy ketone. Now one thing that we can see is that the nucleophile and the electrophile here are both flat. They're both reacting at sp2 centres, but also they're prochiral. Prochiral means that if we were to do a reaction, we would form a stereocentre, and here, because there are two prochiral centres reacting together, there are 2 times 2 equals 4 combinations of possible products out of this reaction. We can see this more clearly by looking at a side-on projection here. The reacting centre is here, circled in orange. As it's prochiral, there is some nomenclature sometimes that gets used here, just using the standard CIP rules, in that the highest priority group will be this carbon attached to lots of stuff, so priority 1. The methyl group will be priority 2, and the hydrogen will be priority 3. And going around those priorities, if we look down from the top, this means that the top face of this enolate is the re face, and the bottom face is the psi face. Don't worry if you haven't seen this terminology before, but it's quite useful for keeping track of things here. So I can react with the aldehyde on the top or re face. The aldehyde is also flat, so for example I could get an attack like this, or I could attack out the bottom face of the enolate and get attacked like that. What I've drawn here is just a translation of the aldehyde, so just moving it without twisting it. And as you can see, we're attacking different prochiral faces of that aldehyde too in doing this. Just assigning the priorities on the aldehyde at the top. Priority 1 is the oxygen, 2 is the R group, 3 is the hydrogen. So that picture at the top is attacking the re face of the aldehyde. The purple aldehyde at the bottom of the page by default is attacking the opposite face, so this is the psi face attack. So when we do our curly arrows, we can either attack like this in red with the 2 re faces coming together, or we can attack like this in green where the 2 psi faces are coming together. Now of course those are only 2 of the 4 combinations that are possible here. To see the others I can just duplicate my diagram and just find the other combinations, and the easiest way for me to do that is to just swap the R primes and the hydrogens here on the aldehyde. And now I've got a picture for every possible reacting combination, and then we just need to work out what the product of each of these attacks would be. So I'm just going to number them. Product 1 with the 2 re faces attacking. Product 2 is when the 2 psi faces attack. Product 3 will be when the re face of the enolate attacks the psi face of the aldehyde, and product 4 when the psi face of the enolate attacks the re face of the aldehyde. So I can just add these to my scheme. Following this picture through for reaction 1, we'll see that the methyl group is down and the hydroxyl group is up. Maybe pause the video for a second if you want to convince yourself that that's the correct 3D. For reaction 2, I will get this product, and we can note that those 2 products are the same diastereomer. Let's just call that diastereomer A. Diastereomer A is of course chiral, and 1 and 2 are the 2 enantiomers of that form. Completing my product diagram, let's have a look at reaction 3 and 4. Reaction 3 will give both of these stereocentres as down, and reaction 4 will give them both as up. We should note that we shouldn't be surprised here by this. We said we'd flip the aldehyde around, and as we can see with this highlighting, the hydroxyl centre has flipped as we've gone left to right. And we shouldn't be surprised by the methyl stereocentre in 1 and 3 being the same, because they're both the re face of the enolate. Same goes for 2 and 4. So in those cases we're using the same face of the enolate and a different face of the aldehyde. These products 3 and 4 are a different diastereomer. Let's call it diastereomer B. And again we're forming this as 2 enantiomers. So if we don't add any more control elements, we're just going to get a mixture of these 4 stereoisomers, and that's not usually very good for anyone. Ideally, I'd like to be able to find a way of picking one diastereomer, either diastereomer A or diastereomer B, and then within that pairing, pick one of the 2 enantiomeric forms as well. And in doing so, we'll have an enantio and diastereoselective reaction, which could be super useful. So the simplest thing for us to do here is to take this in 2 steps. Let's try and select a diastereomer first, and then modify that process to select for one of the enantiomers only. There's actually quite an easy way of solving the diastereoselectivity question, and that's by recognising that this enolate's not going to be on its own. It's probably formed by deprotonation by a base or related processes. And we could engineer this so that there's a metal counterion present in the reaction too. Specifically, it would be good if we had a counterion that's really good at bonding to oxygen lone pairs, because we can remove a degree of freedom in this reaction scheme by making this an intramolecular process, by coordination of the enolate to the metal, but also coordinating the aldehyde to the metal, and in doing so, we'll activate the aldehyde, make it more reactive, and then any intramolecular aldol reaction should be much faster, as in there's no need to wait for diffusion for the two things to come together in the correct orientation, and the transition state here will have the lower energy. So with the facial selectivities, just to map this in, we can set up this locking. Just taking a look at reaction 1, we can see that we've now joined all of this together using 6 atoms. 1 with the counterion, 2, 3, 4 on the enolate, and 5, 6 on the aldehyde. When we get an intermolecular reaction like this, its transition state will be a 6-membered ring, and so we can use the Zimmerman-Traxler model to model this chelated transition state. Just popping down to the bottom right-hand corner, the lowest energy conformation for a 6-membered ring, and hypothesizing for the transition state as well, would be a chair. And it'll look something like this, where at the back, we've just got the enolate, and at the front, there's the carbonyl from the aldehyde that we're going to attack. This is a sort of core skeleton of a transition state. Some things that don't change for any of the reactions are where the R group is. Now it's always going to be coming off an sp2 center during this reaction, so we should probably put it out in this sort of direction. And the enolate geometry was fixed by our selective enolisation at the start. So to have a Z geometry, we'll have the methyl group down here, and that fixes the hydrogen at this position. And there's one final bit to add to this, which is where does the aldehyde put its groups? Now we've got an R prime group or a hydrogen, and it's a really bad idea to put bulky groups pseudoaxial in a transition state because they can sometimes get 1,3 diaxial clash. This might be relevant depending on the size of the R group, but also there might be some ligand or some solvent attached to the metal center too. So we want to minimize the 1,3 diaxial strain, and we're going to prefer to put the hydrogen axial like this and the R prime down here. So in fact, this transition state I've drawn will lead to one of these products. We just need to check which. Now you might be able to see this in your head by taking the perspective of this yellow highlighted sort of wiggle chain. We can see both the hydrogens here and the methyl and the oxygen are pointing down relative to the yellow chain. So in fact what we've got here is the transition state for forming product 3. I can just double check that using the nomenclature. Looking at my enolate face, I've got my priorities 1, 2 and 3, so they're looping around this sort of way. This is reaction coming out of the reface. And looking at the aldehyde, I can do the priorities again, 1, 2, 3, and the attack showed by the dotted line is attacking the aldehyde via the psi face. So all good, I found a way to select for product 3. So just to be super clear on what's going on here, by adopting a chelated transition state and choosing to put my R prime group in the equatorial, I am selecting for the syn diastereomer, which I've labelled as diastereomer B above. If the R prime had been in the pseudoaxial position, I'd be attacking a different face of the aldehyde, so I'd get compound 1, the anti-diastereomer. So the diastereoselectivity here is coming from there being a preference to put the small group pseudoaxial. So it's in our interest for R and L, which are things that can clash with the aldehyde, to be quite large here to maximise the difference in energy for transition state towards product 3 versus transition state to product 1. So now using this chelated transition state, we're able to select for diastereomer B. Not the end of the story though. I'm just going to make myself some space. It's possible to do something similar to show how we get the other enantiomer. So I'm just going to move that transition state to the left a bit. Now bearing in mind that we know that diastereomer B can exist as 2 enantiomers, enantiomers are chemically the same in non-chiral environments, and so we should expect some sort of mirror image to be relevant here. One way I like to think about this type of problem is to just draw the mirror image of my core transition state, just as we did before. Again, we don't have any choice on the enolate geometry and where that R group goes. Making the same choice as we did before, I'd like to put the hydrogen in the pseudoaxial position and the R prime group in the pseudoequatorial position. In terms of clashes and energies, these are exactly the same energy transition state. They're just a mirror image of each other. But if we have a look closely at this, by taking the mirror image, we've changed what's going on with the facial attacks. So with the enolate here, we can see that quickly with the nomenclature, just highlighting the priorities here, 1, 2, 3 as before. Circling around like this means that we're attacking out of the psi face along the dotted line. And on the aldehyde, the priorities will go like this, indicating that we're attacking into the re face of the aldehyde. We flipped both the prochiral centres, so therefore this is the enantiomeric transition state. This is the transition state for product 4. And so some more terminology for this type of thing would be to say that these are enantiotopic transition states, as in they're both the same energy, no difference in activation energy, so under kinetic control they should occur with equal frequency, and so we should get equal frequency of the products, as in a 50-50 mixture of diastereomer B, this is the syn diastereomer, and so we've made some progress. In summary, we found a way to select for stereoisomers 3 and 4, and next we can address the problem, how can we differentiate the reaction that leads to these two by adding something extra to our reaction plan. Now, one very traditional way of doing this would be to use a chiral auxiliary, and before launching into any examples, we can just go through the general idea with the scheme on the screen now. So there's a few ways that we could tweak these transition states so that they're no longer the same energy. One way would be to make sure that the aldehyde has a facial preference for real psi faces for some other reason, such as Falcon-Arm type selectivity. That will mean that one of the transition states on the left or the right will be lower in energy and more preferable, so we'll get some selectivity there. You could also put in certain types of chiral ligand in for L, the detail of which maybe I'll go into in another video. But what I want to focus on here is a really, really robust way of selecting these two, and that's to actually completely modify the enolate and allow our enolate to exert some more control. So just on the left and the right, what I'm going to do is introduce an auxiliary group, just going to call it AUX for auxiliary, put a star by it to remind me that it's chiral, and this is going to help me determine which of these two transition states is lower in energy. So doing the same on both of those transition states. So I put a completely different group of my choosing directly onto the enolate. The auxiliary is chosen to be a single enantiomer of whatever group we pick. That now means that the two enantiotopic transition states become diastereotopic. So you can kind of imagine this like for any diastereomer. On the left, we've got the auxiliary bonded to the re face of the enolate and the psi face of the aldehyde. And on the right hand side, we've got the same auxiliary, but bonded to the enantiomer of the core of the transition state, where we've just flipped both the psi and the re labels. This is sort of analogous to when you're shaking hands, where your left hand might interact well with the left hand of another person if you're shaking hands, but not so well with their right hand. So there's a difference in energy there in interaction. So these two transition states are then of different energy, and the relationship between these two can now be described as diastereotopic transition states. Okay then, so I'm just going to do some tidying up of this screen to go forwards. So right from the start, I've replaced my R group that was originally on my ketone and then on my enolate with my chiral auxiliary. And bearing in mind that the auxiliary group has a single stereocentre in it of the same configuration in both, we've now changed the relationship between 3 and 4. These are now diastereomers of each other. Although the relationship between the methyl group and the hydroxyl group is still syn, the relative stereochemical relationship between the auxiliary and the methyl group is different. So now we form two diastereomers via transition states that don't have the same energy, which are fundamentally different. So we should expect our ratio to not be 50-50 here. The bigger the difference in transition state energy we can make, the more selective we can make the reaction for either product 3 or product 4, whichever one we actually want. Now for this type of auxiliary approach, by far the most famous type of auxiliary is the oxazolidinone, which was developed by Evans. I'll put some links in the description below. And essentially what you do here is I use a chiral auxiliary that looks something like this. So this is just an example of one. If you kind of have a look at this bit of this molecule, this 5-membered ring has come from an enantiomerically pure amino acid. Now that I've got my modified starting material, I can do a selective enolization, and that's pretty easy on a system like this. If I use LDA at -78 degrees, we should be able to get selective Z enolization, as the auxiliary is pretty bulky in the region that I've just highlighted in green. As a result, when we enolise, we can use the island model for deprotonation with LDA, which again goes through a Zimmerman-Traxler type transition state, in that this cyclic deprotonation will have a lower energy transition state if it's a chair conformation. The auxiliary is quite big, and so there's only really space for the hydrogen to go near it, which forces the methyl group into the pseudoaxial position here. Hopefully we can see here that this should get us to the enolate where the auxiliary and the hydrogen are near each other, which is exactly the Z enolate that we need. So now we've got the Z enolate, we can have a think about what the auxiliary actually does in this reaction. The Z enolate here actually has a preferred conformation, which is to orientate like this. And the proposed reason why this is so good is that this will minimize the dipole moments between these two bonds highlighted in green. So all we need to do now is bolt that into the transition state and just replace out the auxiliary label. So on the left-hand side, put my nitrogen in. The nitrogen has two things coming off it. I need to oppose the dipole, so the carbonyl group should go on the left-hand side. Closing the ring will leave me with this isopropyl group just pointing out the back, which is quite nice, and the hydrogen pointing into the middle of the ring. Notice that necessarily this has to be quite planar in this area around the nitrogen. So the explicit red hydrogen there really is jamming into the center of a transition state. Doing the same thing on the right hand side, putting the nitrogen in at the auxiliary position. Again, there's our two bonds that come off there. That nitrogen is sp2. To minimize dipole interactions, I'm going to need to put the carbonyl down here to the right. Closing the rest of that ring will give me something like this. And here's the key bit. When I put the isopropyl group in this time, the stereocenter is going to be the same. So the stereocenter that I've drawn as a star has to have the same configuration all the way through. So in this case, hopefully it's reasonably easy to convince yourself that because we flipped that 5-membered ring over, going from the left-hand transition state to the right-hand one, the isopropyl group will be forced into the middle of the transition state and the hydrogen will be out the back. And this is exactly what we need. So as long as the auxiliary really prefers to sit in a certain conformation, like this one does, we're introducing a really big bulky group into the center of the transition state here for the one on the left, whereas the one on the right only has a tiny hydrogen. For all the standard reasons with 6-membered rings, that means that the transition state on the left-hand side will be lower energy, and that will mean that product 3 becomes the major product. And if we're unlucky, we might see some of product 4, and this becomes the minor product. Now, for these Evans auxiliaries, it turns out this reaction is incredibly selective. One of the most diastereoselective reactions I think I've ever done. You're talking well above 20:1 selectivity for the major diastereomer out of this reaction, to the point of seeing very little of the minor one at all. This reaction is really scalable and pretty operationally easy. So it's really cornered the market if you need to selectively form a syn aldol product with specific configurations at your methyl group and at your hydroxyl group. So if we're going to take this approach, now that we've formed the stereocentres, we're going to need to do some additional chemistry to get rid of the auxiliary. It was only there to help us set the stereocentres, and normally we'd want to get rid of it. Luckily, there's some standard procedures for doing this. Let's just get rid of this transition state for product 4, which we've now worked out is the minor product, and double check where we are. When we draw it out in full, our intermediate's going to look something like this. There's quite a few simple transformations we could do. It's pretty straightforward to hydrolyze to the carboxylic acid, and the conditions we need for this are lithium peroxide and then a reductive workup, so e.g. sodium sulfite. Perhaps seems a bit of a weird choice, as in why haven't we just used the hydroxide? Now the hydroxide is just a little bit too basic for this. So other things that the hydroxide could do is deprotonate the product and set up a retro-aldol fragmentation, something like these green arrows. Another thing, if it's too basic, would be a potential risk of enolisation of the newly formed stereocenter that we put a lot of effort into. So there's a risk of undoing all of our work here. And it turns out that this peroxyanion is just a little bit less basic, but still pretty nucleophilic. To perform the hydrolysis along this sort of lines, the peroxy acid is then reduced to the carboxylic acid by reduction in the sodium sulfite workup. Another super useful thing that you can do is to convert the product to the Weinreb amide. This can be achieved just using the standard amine in the presence of trimethylaluminium. Now specifically why we need that aluminium Lewis acid in here is because that will react with our free hydroxyl group, releasing methane and chelate up the starting material, something like this. which then activates the carbonyl that we want to attack really nicely and allows us to do this transamidation type reaction. So swapping one nitrogen for the other. A few proton transfers in there too. The Weinreb amide itself is really useful because you can transform it using a Grignard reagent into, say, any ketone you like. A Grignard will only react once with this Weinreb amide. It won't add again to the ketone product. Of course, you'll also have to put a protecting group on that hydroxyl if you're going to do that sort of thing. One final thing that we could do with this product would be to just treat it with lithium aluminium hydride. Again, it's best that we do this while there's still a free hydroxyl group, because that allows some pre-coordination of the reagent to direct the hydride to the carbonyl that we want, and after a couple of steps similar to this, it gets us this diol product for future use. Now in all of those reactions, we also release our oxazolidinone, the idea being that all of those methods are non-destructive for this group. So we should be able to separate this, maybe with a column, and recycle the auxiliary next time we want to do an auxiliary controlled reaction. Now, although using the Evans auxiliary really is normally a good idea for this type of reaction, enolates that have this type of auxiliary attached normally completely override any other selectivities going on in a more complex transition state, but it's worth being aware that this isn't the only auxiliary out there. I want to introduce another one, mainly to show that this idea is more broad. A ketone with another useful auxiliary attached to it is something like this. So the ethyl ketone with this type of stereocentre on the left-hand side. So here I've got a benzyl ether sitting on a new stereocentre, just highlighted with the green star, which also bears a methyl and a hydrogen. This is often referred to as a lactate auxiliary, and that's because it's based on lactic acid, which has this structure. We can play the same sort of games as before, just using some slightly different reagents, but the underlying principle is the same. What you'd normally do first is react this with cyclohexyl boron chloride in the presence of triethylamine. So you may have seen this boron reagent before, but here it's going to be doing something slightly different to normal. I think the best way to look at this is it's a Lewis acid, which also has a leaving group. So you can potentially chelate up with this, and that's exactly what we're going to do here. If we have a look at our starting material, we've got lone pairs on our benzyl ether and on our carbonyl. Both of them are available and they're a nice number of atoms apart. So we should be able to set up some sort of chelate like this, and this is going to help us get the selective enolization step working. We need to be able to remove one of these green protons, and to work out which one is best, we need to think about what conformation this molecule adopts. For us to be able to deprotonate next to any carbonyl at all, just with a general group here, we require this type of orbital overlap, where the CH that gets deprotonated must necessarily be at right angles to the plane of the carbonyl group. That gives us a good interaction between the sigma bond and the pi star, which allows us to form our enolate when we deprotonate. So in this particular scenario, we're going to need a quick 3D sketch to see what's going on. I need the hydrogen that I'm going to deprotonate to be perpendicular, and just sketching the rest of the chelate in. When we have our activated carbonyl like this, where the green proton is more acidic, the group on the auxiliary helps us pick the enolate geometry. So the key interaction that we're looking for is what do we want to put that could potentially clash with that methyl group, just in a steric sense, versus what do we want in this empty space over here. So the best option for deprotonation will be the green one, where the methyl group is over on the right hand side and the hydrogen is over on the left. So this just minimizes the steric interaction. So out of all the possible conformations, the lowest energy one will be this one. If we look carefully at this structure, when we do the deprotonation, we can sort of see a little zigzag in it, which shows us that we'll be getting the Z enolate with this one as well. So taking this back into our structure, we can use our auxiliary here to get that control for us using soft enolization conditions. So before we used LDA, where the base is going in directly, here we're using a Lewis acid to make some protons more acidic and using a weaker base. Now this might be good for us in more complex molecules because these conditions are milder and tolerant of other functional groups in a bigger molecule. Next we can chuck in our aldehyde and do an Aldol reaction with this. We can see that the bidentate chelate is not the strongest in the world, and it's possible to satisfy that boron center by using the oxygen lone pair on the aldehyde as well. So I figure in equilibrium, we have this type of structure which can coordinate onto our aldehyde. which gives us the activated system like we had before to allow us to do an intramolecular aldol through a lower energy transition state, both because the aldehyde is activated and the process is now intramolecular, which also helps with the rate of reaction. If we follow through to a transition state, we can use exactly the same sort of logic as before, because we notice that the auxiliary has a polar bond, just like the Evans auxiliary, right next to the enolate. So there is a preferred conformation where that CO bond opposes the CO bond in the enolate. Our transition state will end up looking something like this. That's the core of it there. We didn't have any choice on the enolate geometry, we've got the Z enolate. As per usual, we probably want to put the hydrogen on the aldehyde in the pseudo-equatorial position, especially when we've got these bulky cyclohexyl groups on there now. That's really causing a problem for 1,3 diaxial interactions. Our prime goes down in the pseudo-equatorial position as a result. And then just building in the auxiliary, an sp2 center comes off the ring first, because that carbon's always going to be sp2. We oppose the dipole, like so. This is our preferred conformation of the auxiliary. And in doing this, the stereocenter is projected like this. So for this transition state, the methyl group is out the way, and this is the best possible option. If we were to draw the diastereotopic transition state, the red methyl and the red hydrogen would be the other way round. That transition state will be higher in energy and maybe will lead to a minor product. So what we actually get with this system is exactly the same product as we get before, just using a different system. So why might we want to do this, you ask? Well, we're not getting any extra selectivity here. In fact, the Evans aldol is usually superior in terms of diastereoselectivity for the reaction. Using the lactate auxiliary isn't bad by any means, 8:1 to 10:1 DR in most simple systems. But the difference lies in what you might be able to do with it later. So you can manipulate that lactate auxiliary into many other things. Perhaps have a think to yourself and drop some ideas down in the comments below. Another reason why we might want to use this auxiliary is that we might want that stereocenter in our final product anyway, in which case it's not really an auxiliary, it's just part of the molecule we were trying to build. But the main reason for me bringing this up is that I've spent this video completely ignoring different product diastereomers. I've focused here on techniques to make the syn diastereomer across the newly forming carbon-carbon bond in an Aldol reaction, but we might want to make the anti one at some point. We should at least have that in our toolkit. We run into a problem if we try to use these ideas in the same sort of way. If I wanted to do this via a chelated transition state, using the Zimmerman-Traxler model, I'm necessarily going to need the E-enolate. Now there are a couple of things we need to address, is that we need a way to make that selectively. Now the problem doesn't really come in making the E-enolate. There are plenty of selective enolization methods that can do this. The problem comes when we try to do the Aldol reaction itself. If I just draw in my transition state core again, I now have a slightly different situation because my methyl group is in a different place on my enolate. And this is going to cause us some grief because it's quite bulky and being held coplanar to this bond, which is where the auxiliary is going to live. So for example, if we try to use the Evans auxiliary, we start to get into a bit of a problem because all of this is going to start clashing. And all of a sudden, the conformation of the auxiliary that was going to give us good diastereoselectivity has been completely ruined. There's every possibility it's going to need to sit in a different conformation to the one that we need. We can't avoid this with the lactate auxiliary either. Using the same logic, we would still get the clash. Maybe here a bit more explicit to be able to see that this clash would sometimes be referred to as an A1-free strain interaction, or allylic strain, which we'd normally describe using the Hauck model. The main consequence of this is that we can't sit in a nice distinct conformation. We'll just get lots of different ones available to us of similar energy, and this is a recipe for low diastereoselectivity, so we'll get a low DR of product, and no one needs that. So how are we going to unpack this? Well, I'm going to address this anti-aldol problem in my next video, so please stay tuned.